Okay, thank you, Magdalena. It's a pleasure to be here with you, and I hope I will go back to Prague very quickly, but I'm sure that I will go there. So today I will speak about green synthesis of eco-compatible ionic liquids, and we will see today the synthesis of this ionic liquid and also the use of this one in the field of the extraction of the solubilization of biopolymers. And you will see one or two slides of preliminary result of our PhD student, which is in co-tutel between Prague and Reims. And after that, if you have some question, no problem about that. So I will begin. Ça marche pas. Yes, I will begin, yes, now with the definition of ionic liquid. In fact, ionic liquid are an association of organic anion and an anion, organic cation and an anion. So the properties of this ionic liquid in general, that is a melting point, which is lower than 100 degrees, a high solubilization power, thermal and chemical stability, and also what is very important here, it is low vapor tension. And in fact, you have a large diversity of structure. You can have some ammonium, some imidazolium, some phosphonium, some sulfonium, and so on, and as a cation, for example. As anion, you can find some halide from bromide, chloride, and so on, or some more complex fluoride anion, for example, this one. And sometimes you can have also some organic anion, for example, here carboxylate, or as well as acetate or sulfonate, for example, here. Concerning now the application, you find a lot of applications since many years in organic synthesis, catalysis, separation, complexation, and most of the time also in electrochemistry and in the field of the energy. So at the beginning of this project, in fact, we were interested to build some biosalts, ionic liquid. And here, why? In fact, the problem of ionic liquid is the toxicity of these ionic liquids. In general, they are not biodegradable. You use, for example, the method 301 here of the closed bottle test. And here you measure the consumption of O2 or the production of CO2. And if you have a percentage higher than 60%, you can say that your ionic liquid is biodegradable. Moreover, usual ionic liquids are also ecotoxic. And that is a problem here if you want to use this ionic liquid as solvent. So at the beginning of the work here in Reims about ionic liquid, I collaborate with Nick Gathergood. Nick Gathergood was, first of all, in Ireland, next in Tallinn, in Estonia, and after that, he is now in Bath, in the south west of London. So at the beginning, we wanted to see the use of more biodegradable ionic liquid. So Nick showed that that was possible to modify some imidazolium here by here an amine, for example, an amide, for example, or here an ester, and here an ester with here polyoxygenated chain. And here, with this kind of ionic liquid, you show that the biodegradation here, for example, is the percentage of biodegradation is 54%. Here it is really not good, but concerning this one, associated to this kind of anion, we can have a biodegradable ionic liquid. So we wanted to see if modified imidazolium could be used as solvent for hydrogenation. So we saw that was possible, and here that was more selective in a monohydrogenation of this chain with two double bonds here. So after that, I decided to work on biosource ionic liquid. First of all, with here anion coming from the biomass to see if we could have some potential biodegradability and also a lower ecotoxicity. So at the beginning, we used some tetrabutyl ammonium as cation, and we associate this anion, this cation, to carboxylate coming from acid. These acids are coming from biomass. Here you have, for example, the lactic acid. Here the tartric acid. Here, for example, the pyruvic acid. And here you have sugar-based acid. You have glucuronic acid, and here galacturonic acid. So we built some ionic liquid through a very simple reaction here in water or in ethanol at room temperature or at 100 degrees during 24 hours. But in fact, in six hours, the reaction is good also. And we build this kind of ionic liquid. So here you see good results and as yield. And here you have the aspect of this ionic liquid. For example, here, for this sugar-based acid, we obtain for the TBA glucuronate or galacturonate some solid, but the melting point of these solids were under 100 degrees. Here, concerning now some physical properties of this ionic liquid. You have here the viscosity at 25 degrees, but here at 80 degrees. And you see that, for example, for this TBA lactate, you have a weak viscosity here, but a high viscosity, for example, for tartric or malonic derivative ionic liquid. You have here the glassy temperature, the glassy transition temperature. It is negative here, but here it is positive for this kind of ionic liquid. And here you have the composition temperature around 200 degrees Celsius. After that, we wanted to see if this ionic liquid were biodegradable or non-ecotoxic. So concerning the ecotoxicity, that was in collaboration with Nick Gathergood, and I will speak after that. Now we can do that in Reims with another laboratory of the university. And here we study the toxicity on several strains. You have here 3 strains, but we have realized the experience on the 15 strains here. So here you have TBA bromide, TBA hydroxide, and here our ionic liquid. And you see here that in general, our synthesized ionic liquid are less toxic than commercial ones. Concerning the biodegradation, here you see that the most percentage of biodegradation is 23. So our ionic liquid are not biodegradable, but when you compare with here some TBA bromide, for example, or TBA hydroxide, it is more biodegradable. So next, just an example of use of this ionic liquid that was in catalysis for the selective hydrogenation of unsaturated compounds, for example, here for this cyclooctadiene. And here we obtain this monohydrogenate compounds. And here you see that that was possible to recycle this ionic liquid. Here you have 10 cycles, and here it is a result without ionic liquid. So that was here this example of TBA succinate, but we use a lot of TBA derivative and obtain around the same example. Next, we have extended this hydrogenation to selective hydrogenation to fatty acid, and that was also good results. We extend also the method of synthesis with proline-based proline-based ionic liquid, and we obtain here this kind of TBA prolinate, the two forms of prolinate, and here with this hydroxy prolinate. We showed also that this compound were also good chiral additive, with also a co-solvent for the problem of viscosity of this ionic liquid for enantioselective hydrogenation of alpha-beta unsaturated ketone under mild condition, because that was really low temperature and also very quick times. We then extended the study to not to ammonium cation, but to phosphonium cation. And here, with the same reaction, we obtain a different kind of tetrabutyl phosphonium compounds. We showed that this ionic liquid were not biodegradable, but they show also no ecotoxicity. So that was really important in that. And we use that, this ionic liquid in Heck reaction for just carbon-carbon coupling. So we wanted after that to have an ion coming from the biomass, but also cation coming from the biomass. And we wanted after that to use this ionic liquid for biomass solubilization, biopolymer essentially, cellulose or lignins, and also extraction of bioactive agent. And you will see how we will prepare this new ionic liquid and the different, some example of different use of this one. So here, that is the general procedure to obtain this biosource or bio-based ionic liquid. From here, the choline, and here you see this one. This one is the choline, and the choline is coming from yoga, soja, and also some different kind of human residues. And here, coming from the choline, you see you have an ammonium coming from biomass. And here you have, for the first reaction, you build an ester here on this OH group. You build an ester. It is an esterification reaction in the presence of this acid. And after that, you have a first metathesis, anionic metathesis between this chloride and this perchlorate to furnish this kind of ionic liquid. This step is essentially, why? Because it is more easy here to separate and to purify this perchlorate than this one. After this one, at the purification of this one, you can realize a second anionic metathesis to exchange this perchlorate to, here it is the lactate, and here it is a levulinate. And it is very easy to do these two anionic metathesis to obtain this. The yield are overall between 60 and 90%. and we will see how to use these compounds. First of all, some characteristic of these ionic liquids. You have here shorter chains with 6 carbon, 8 carbon, and after that you can have 6 carbon and 12 carbon. So here you have oils, and after that you have wax because you have a longer carbon chain on the ester. And the degradation temperature here are around 200 degrees, 250 degrees. Concerning the viscosity, at 60%, we measure that here for this small, longer carbon chain. And here that was not determined because it is very viscous at this time. So first, that was the extraction. The first use was the extraction of bioactive compounds. This I will show you the extraction of curcumin. Curcumin is coming from curcuma, and this curcumin, you have 3 types of curcumin, and that can be extracted by solvent as, for example, alcohol, methanol, ethanol, isopropanol, or here from acetone. And you have here the possibility to extract this curcumin at 60 degrees during 30 minutes. These curcumin are anti-cancer agent, but they have also some antioxidant, anti-inflammatory, and antibacterial properties. So the procedure is relatively easy. In fact, you take some curcumin longa powder, 2 grams, and you take 3 milliliters of ionic liquid. I will show you which kind of ionic liquid we used and with which kind of ionic liquid we obtained the best result. Here, during 30 minutes, 70 degree, you have the dissolution of this one. After that, you add some water. I don't say it before, but all ionic liquid we synthesize with TBA, TBP, and also with choline-based ionic liquid are hydrophilic. So you can add some water to fluidify also this ionic liquid. So you add some water, and after that you add an organic solvent. It could be ethyl acetate, or it could be more greener, a greener solvent as methyl THF, or here gamma valerolactone. But the best is methyl THF because gamma valerolactone is relatively viscous. And after that, you have 2 phases. The organic phase, who are containing the curcumins, and also an aqueous phase, which contain, in fact, the ionic liquid. And if you have this ionic liquid in the aqueous phase, you can, after that, evaporate the water and reuse your ionic liquid. So that was you will see after that the main result concerning curcuma, but to be sure that we have extended this method to other bioactive agents, for example, carvacrol from Oregon, and we obtained also a patent with Jean-Pierre about this kind of procedure. So here, concerning the extraction of curcumin, you see that here you have the result with acetone. With acetone, in the same condition, you have the extraction yield of 9%. And here, that is with the MIM BF4, this ionic liquid, you obtain 11%. With our ionic liquid, we short chain here C6 or CH, you have not more than with this one, you have around 12, 15%. but here with longer chain and with lactate. Lactate is less lactate give a lower viscosity than levulinate as anion, and you can see here an extraction here yield of around 30%. So the second use of this ionic liquid is to solubilize some biopolymers. So I will show you what were our results concerning the dissolution of microcrystalline cellulose. And if you have some question concerning other biopolymers, we do the experiments also with lignin, and that is the purpose also of the PhD of mass 1. So to solubilize some biopolymers, you will have attention, you must have attention on the role of the anion and the cation. The anion here, as you can see in this slide, is to have some hydrogen bond with this OH coming from the cellulose. And the role of the cation is also to coordinate this oxygen atom in order to have a weaker hydrogen bond. So for the microcrystalline cellulose, you have here the result concerning the different ionic liquid here. Here you have the procedure. You can take some choline, and here choline-based ionic liquid with choline, and here you have a C8 chain, and the anion was levulinate. You take that, you warm that during 1 hour at 100 degrees, and you obtain this kind of mixture. After the filtration, because all the cellulose is not dissolved, in fact, you can have, you can use some ethanol and water, and you here you obtain some regenerate cellulose. So here on this diagram, you see that with this choline C8 levulinate, we obtain a percentage of regenerated of cellulose of a percentage of dissolution of this microcrystalline cellulose of around 30%. Here at the beginning, you have 8% with this enime acetate, okay? And with other B- Cl, for example, it is a very famous ionic liquid for the solubilization of cellulose, you have 20%. Concerning the physical characterization of this cellulose, when you have the treatment of 1 hour, of 2 hours, or 2 or 3 hours, you can see here by XRG that you have a loss of crystallinity. When you have a treatment of one hour, you obtain 80% of microcrystallinity, and this percent is decreasing when you treat the cellulose and microcellulose during 3 hours. So I told you that was possible to dissolve also lignin, just to inform you that we obtain around 40% of dissolution of lignin, which is also a good result compared to the result described in the literature. So just here, 2 slides concerning the beginning of the PhD of Maasoa Souvenir in co-tutel with Magdalena. So in the field of the dissolution of biopolymer, in fact, you have most of the time, you have water in the medium. So that is the problem to also to understand the crucial role of water in this mixture. So Masoa was in Prague during 6 months last year, and she wanted to study the physical properties, the thermodynamical properties of ionic liquid, our ionic liquid, and also mixture of our ionic liquid in water. So here it is not our ionic liquid, it is just a model. It is a phosphonium with a prolinate. And here he wanted to see how was the density, how was the evolution of the density in function of the temperature for this sample. And she saw that the density was lower when the temperature was higher, which is normal, in fact. And the behavior of this ionic liquid could be considered as an organic solvent. That was here for the density. And she measured too, also by DSC, different glassy temperature. And she saw that was around here, you have this temperature here, this one and this one, around minus 62 degrees. Now, we wanted, now she's familiar to this method, and we wanted to test essentially this choline C8 levelinate, or also some other ionic liquid with a double chain at the end of this of the carbon chain, and this double bond could also be used to have Bola-form ionic liquid, in which we can also do some catalysis, micellar catalysis, for example. So I show you that that was very easy to do this ionic liquid, this TBA, TBP, or also choline-based ionic liquid. We have also all the physical chemical characterization of this ionic liquid. They are not biodegradable. Even the choline-based ionic liquid, but they are really non-ecotoxic. That is very important to do for this ionic liquid to be used as potential green solvent. You saw also various applications in catalysis, in the dissolution of biopolymer, and in some extraction of bioactive compounds. So now we want really to extend the study on the thermodynamics of pure or mixture with water of this ionic liquid, and also extend the solubilization of other biopolymers. We have an INR project with people from Nantes, and we are working on paramylon, which is a polysaccharide coming from microalgae, and extension also to the extraction of other bioactive compounds or essential oil, which could be also of interest for an industrial development of our ionic liquid. So I will thank you for your attention, but also I will thank Jean-Pierre and Safa and Masoa. Safa has also a lot, has worked about phosphonium ionic liquid, and she was also in the lab during some years for, yes, until next year, until the year before. And Masoa is beginning this PhD with Miss Magdalena in Prague. So here our collaboration with Nick Gathergood, with people from Amiens, where we previously realized some physical application, and also we thank Magdalena for the good work with the Masoa until now. Some financial support, okay, and I will also thank the PhD background and also the Ministry of France to provide some support, financial support for our lab, and I hope for Marsoa too. Here you have some a view of Reims. You have snow here, but we didn't have snow since 2-3 years now. Here the cathedral where we are going when the reaction do not occur. Here the Hôtel de Ville, and here our lab here with a lot of green field and so on. And so I want to thank you for your attention. And if you have some question, don't hesitate to ask me. It will be a pleasure to answer you. Thank you.
Thank you, Sandrine. So I'm sure there will be questions, so don't hesitate to raise your hands, perhaps here in the room or even online. Yeah.
So if I can raise the hand, I would like to ask, or thank you for a nice presentation. And I would like to ask about this set of anions, this lactate and levulonate, or how it's called. There was a tendency that these two had the ionic liquids derived from these two differed in thermal degradation or in thermal stability, and they differed very systematically. Do you follow this this logic in some way, and maybe are you about to use it? This systematic dependence of thermal decomposition, or this temperature of thermal decomposition on the composition?
Well, we didn't have a lot of information concerning now the thermodynamic properties between lactate and levulinate. But what I can say, that is, with this levulinate, we have less viscous ionic liquid, even if you have here a longer chain. With levulinate, you have a more important viscosity concerning this ionic liquid. But what is important, that here with levulinate, when you take the bimime, butyl methyl imidazolium, with levulinate, if you saw in the literature, you can see that the bimime with levulinate is biodegradable. So the importance of this anion could be also in the field of the biodegradation, even if you have a more viscous compound. Well, if you have a more viscous compound, you can use a co-solvent. And the properties of our ionic liquid is the fact that we can use some water associated to this ionic liquid. So it could be interesting to use this levulinate ionic liquid, but by addition of water. So the determination of the proper thermodynamic properties is crucial for pure for this pure ionic liquid, and also with this with a mixture with water. And so I hope we will have some good relationships between the thermodynamic properties and the use and the behavior for solubilization or extraction. But here you see that we have a double bond here and not here. You have no always just an OH. So the difference is coming from here. You have two carbon, two CH2 more, but I think the most difference is coming from this here, from this presence of hydrogen here and not here.
Okay, thank you. And maybe could I follow with another question? You have mentioned repeatedly that you measure also glass transition temperature.
Yeah.
Does it have any like direct application, this information about glass transition temperature? Do you sort of optimize the glass transition temperature, or is it rather just a characteristic of your ionic liquid?
Well, in general, when you want to publish some new ionic liquid, you have to present all the classical value or determination of this ionic liquid. But concerning the glassy temperature, it also depends if your ionic liquid is pure or not, and we can also have some crystallization in presence of water. And I don't know, it could be interesting or not for our dissolution, but I think it could be crucial to know if we have evolution of this temperature in the presence of water. And I'm sure it could, it will be, we will have some differences, in fact.
Thank you.
Okay, thank you. Are there any other questions? Maybe I could just add to this, to Sandrine's answer on glassy temperature.
I'm sure.
It's more of our field. So for the organic synthesis, this is a crucial material property because it determines the liquid range of your compound. On the other hand, for us thermodynamicists, it could be interesting from the fundamental point of view, because if you try to see how the phase transitions and glass transitions evolve, if you add some solvents, and how you modify the glass transition by modifying the structure of your compound, and perhaps also the kinetics behind this. This could be very interesting, but this is more of this thermodynamic subject that is interesting to us. It's not, let's say it's not useful in terms of applications, but it's very interesting in terms of beautiful thermodynamics. Are there any other questions? Eva, yeah, Muchova.
Thank you for the presentation. Can you hear me? Is it okay?
Yes.
Okay.
Yes.
So I would like to have a follow-up question of what Andra said about this slide. So I can see on the left side that the lactate and levulinate anions are pretty similar. So do you have any idea why one of them is biodegradable and the other one is not? So is there any mechanism which is responsible for the change of behavior?
I think here I didn't have they didn't have the answer in the publication, but here you have the possibility to cut here, and the double bond here is very important with the relation with the different strains, and it is more suitable to have a double bond with an oxygen than this one. I think with this one, it is very easy to cut this double bond than this one, because here you have hydrogen bonds with different kind of support of strains and so on. But in the papers, there are also surprised with the behavior of this levulinate. So I didn't have no more answer about that.
Sure, I was just wondering if there is any mechanism which is responsible.
Yeah.
It's going to be found in the following years. Okay, thank you.
Yeah, I think so. I hope so.
Okay, does anyone else have a question? I may ask actually something that we've already discussed with Sandrine, so this is not going to come to her as a surprise, but could be perhaps interesting to other people listening. We were talking about choline just recently, and about the possibility to obtain it from soy, for instance. How difficult it is to obtain choline from such bio sources, because right now, let's be honest, we use what we buy from a manufacturer. With this in mind, that potentially we could think of ways of obtaining it from real biomass. So how difficult it is to obtain choline from soy, for instance?
So at this time, they are using some typical extraction with organic solvents. And the purpose of the study here could be also to use our ionic liquid to extract this choline from soya. So it could be, we could have some interaction perhaps to favor the extraction of this one. Because at this time, only organic solvent as ethyl acetate, for example, or acetone are used to extract this choline from soya. So I discussed with industrial for 2 or 3 months, and they didn't want to have ethyl acetate as compounds for extraction. They prefer to have methyl THF or this gamma valerolactone, which is a greener solvent, but the viscosity of this one is really high. So for instance, we didn't have any more, we didn't have any eco-compatible process to isolate this choline from soya.
Okay, thank you. Jan has a question.
Jan?
Okay, yeah, I have one question regarding the mechanism, how the ionic liquids should dissolve the cellulose. If you could go to the slide where you have shown the hydrogen bond, yeah, this one, right? So here you show that the cation and anion should operate through some hydrogen bonding to the OH. So then if we go to the slide where you summarize the potential, or how much do different ionic liquids solubilize cellulose, it seems to me that the more potent are those which have longer alkyl chain. So I think
this one?
Maybe there was one more. There was a table with.
No.
Just before that.
Yeah, that was.
Okay, sorry. This was
curcuminoids.
Okay, but on the if we go to the cellulose. So
yes.
Okay.
This one.
Right. So. Okay. So is. Well,
I don't hear you, Jan.
Yes, sorry. So.
Yes, it's better here.
Yeah. So I wonder, is there some trend with well, I don't know if the ionic liquid is more polar or if it is more.
Yeah.
Or.
Yes. It's more. In fact, when you have this C12 this C12 compounds, in fact, you have a more organic solvent, and you didn't have some amphiphilic solvent. It is sometimes very difficult to solubilize this one in a small amount of water. Okay, so here you have really a problem of amphiphilic character and also on viscosity, because you have here this C12, you have levulinate, but you have this C12, and it is a big compound. But if we go here for the extraction, we wanted to extract this kind of really pure organic compounds. And this one, these compounds, curcumin 1, 2, and 3, are not water soluble. Here you see that the best results are obtained with longer chain. And it is just a proportion, just an equilibrium between the solubility in water and the solubility in organic phase.
Okay, I see. Oh, okay. Thank you.
Yeah.
Okay, thank you. Some more questions. Okay, if not, let's thank our speaker again, and let's hope that in a very near future, Sandrine will be able to arrive to Prague.
Yes, no problem.
Okay. So thank you very much for joining us, and
Thank
hopefully
you.
soon enough.
Okay.
Ne, to je potlesk. Eva
Okay,
is
thank you
clapping.
very much.